Here we're going to look at quite a difficult calculation involving Kp. I've been told I've got a mole of nitrogen, 3 moles of hydrogen. They're mixed together and allowed to reach equilibrium in the presence of a suitable catalyst and a total pressure of 10 atmospheres. And I'm telling you that 15% of the equilibrium mixture contained ammonia, and we've got to find Kp. Now there is numerous ways of going about doing this, but I'm going to show you sort of the conventional method using Rice tables. I will show you at the end a kind of a bit of a shortcut method as well. So first thing I'm going to do is set up a Rice table. Now I'm also going to add another little column here which is going to say total moles. So what I've been told then is I've got 1 mole of nitrogen, 3 moles of hydrogen, and we always again assume that if we're not told otherwise, we've got 0 moles of products, and that gives me a total number of moles at the start at 4. Now the change, this will go then down by X, and for every mole of nitrogen that reacts, 3 moles of hydrogen react. So this will go down by minus 3x, and this will therefore, for every mole of nitrogen which reacts, 2 moles of ammonia is formed, and therefore this is going to increase by 2x. So if we just have a look here, we've got an increase of 2x but a decrease of 4x. So the net result is the total number of moles has gone down by minus 2x. At equilibrium then, I've got 1 minus x. I've got 3 minus 3x, which you can simplify 3 minus 3x to be equal to 3 brackets 1 minus x. They're equal to the same thing. I'm just going to scribble that out, put that on there. And then the moles of ammonia is going to be 2x. The total moles at equilibrium then is going to be 4 minus 2x if we follow the same procedures as we've done before. So what we need to do then is work out mole fractions. Now from this bit of information here, we can work out the mole fraction of ammonia. 15% of the equilibrium mixture is ammonia. What that is also telling us is that the mole fraction of ammonia must be 0.15. So we know the mole fraction of ammonia is 0.15. Now what is the mole fraction of ammonia? It's the moles of ammonia, which is 2x, divided by the total moles, which is equilibrium 4 minus 2x. And we know, because the question tells me that the mole fraction must be equal to 0.15. And it's simply now a case of solving that for x. So we'll do that very, very quickly. So we've got 2x divided by 4 minus 2x equals 0.15. So let's multiply both sides by 4 minus 2x. So that gives me 2x equals 0.15, 4 minus 2x. 2x then equals, that will give me 0.6 minus 0.3x. So 2x plus 0.3x equals 0.6. So that says 2.3x equals 0.6, and therefore x is 0.6 divided by 2.3. And when you do that, you should get 0.261. And that's equal to x. Now, the point of that is that we can work out the mole fractions of my other components in the mixture. So the mole fraction of nitrogen is the moles of nitrogen, which is 1 minus x over 4 minus 2x. And when we call x 0.261, we get an answer of 0.2125. So that's the mole fraction of nitrogen. And I can repeat that, working out the mole fraction of hydrogen. Which is and again, we need to substitute 0.261 for x, and that would give us an answer of 0.6375. So that gives me the mole fractions of each component in the mixture. I've highlighted that there in yellow. We need to then get the partial pressures of each of these, and remember that partial pressure is mole fraction times total pressure. So the partial pressure of ammonia is going to be equal to 0.15 times 10, which is 1.5. The partial pressure, I'm just going to cut and paste these, or copy and paste to save time. So the partial pressure of nitrogen and that's going to be, well, let's see what the nitrogen was. Nitrogen is 0.2125 times 10, and that gives me 2.125. And the partial pressure of hydrogen and that's 0.6375. Again, times that by 10, and that'll give me 6.375. Remember that all these partial pressures here should add up to the total pressure of 10. And it is just now a case of plugging that into my Kp expression. So Kp, remember, is equal to the partial pressure of ammonia squared divided by the partial pressure of nitrogen, the partial pressure of hydrogen cubed. So Kp then is equal to 1.5 squared divided by 2.125 times 6.375 cubed. And when you do this calculation, you should get 4.09 times 10 to minus 3. And the units for these will be atmospheres to the minus 2. And that is your answer. Now, that is kind of the step-by-step method of how you do this. There is actually a simpler way to do this, which I'll tell you now. Now, you'll get the same answer. Now, you've been told, or you know, that the mole fraction of ammonia is equal to 0.15. And you know that the mole fractions should all add up to 1. You also know, based on this ratio here, that the number of moles of hydrogen is always going to be 3 times that of nitrogen, always. So you know then the mole fraction of nitrogen plus hydrogen has to equal 0.85, and that the mole fraction of this has to be 3 times the mole fraction of this. So when you do that, the mole fraction of hydrogen then is going to be equal to 0.85 times 3/4, and the mole fraction of nitrogen is going to be 0.85 times 1/4. And when you do that, you do 0.85 in your calculator times 3/4. Lo and behold, you get 0.6375. And this is 0.2125. So you get the same answers as you would have done if you do these calculations here. Obviously, this is a little bit easier, but this is kind of this is just an additional method using Rice tables. But this one is one that you may find a little bit easier to grasp. As I said, both will give you the same mole fractions, and again, once you've got your mole fractions, you need to work out partial pressures and then plug them into your Kp expression.